say?
Down the bridge.
Explain the analytic viewpoint.
Okay. Well,
Now we can go back.
right. Just wait. So thanks for asking me to do this. Well, so I mean, this is supposed to be about singularities. I don't know how much I know exactly about singularities, but there's certain kinds of ideals and are very nicely inspire analytic methods. So that's what I'll try to explain. So, well, I'm going to move away from algebraic geometry, from algebraic language as soon as I can. Okay. Well, if you have some ideal, it's usually described by a bunch of generators. So take some germs of holomorphic functions. And I guess the analytic approach to studying the common zero locus of these is to look at this function. And this is a certain kind of function called a plurisubharmonic function, which I'll define more precisely in a minute. But so one of the things you could do is you could, for example, look at the set of all germs so that this function is bounded. So this is just the integral closure of the ideal generated by these FIs. And so some kind of what you might call an analytic condition defines that integral closure.
That's supposed to be obvious?
That it's the integral closure?
Yeah.
I think it's some kind of exercise.
What closure means? What does it mean?
I mean, it's a set of all solutions of certain polynomial equations with coefficients in the ideal. So, but this is what I usually take the definition of integral closure to be. So. Right. So this ideal, of course, describes everything about the common zero locus of the FIs. I mean, if it's integrally closed. But we're looking for more particular information about the singularities, and we might want to.
It's a big jump between
Yeah.
bound and an algebraic thing. So.
I mean, that's why I said I want to move away from the algebraic language. I mean, you want to just look at this collection of objects as clearly an ideal. And so you just collect them all, and they contain all the information about the common zero set.
I see.
What kind of functions are you considering?
Holomorphic germs.
Germs.
So P is
Just-
a point.
Yeah, P is just some point. So germs of holomorphic functions in a neighborhood of P. So P is some point in Cn. So, but this ideal is not going to, we're not going to be able to extract a lot of information.
Don't blow up at the point, so it's obviously an ideal.
That's right.
Okay.
Yeah. But we want to get some information about where not only these are all zero, but also the thing is singular. So and maybe it's a little easier to look at a little bit bigger ideal. So we can finally define the multiplier ideal. So kind of a bigger ideal is this one, I of phi. So this is going to be the set of all G, so that, well, you relax a little bit the condition of being bounded, and make this locally integrable. So this is called a multiplier ideal. I mean, these ideals actually, there's various versions of them, and they came up in analysis originally because people were trying to study certain kinds of differential operators, and they look at their symbols, which is something characterizing the leading order terms, and to see how much it degenerates. I mean, this ideal will usually capture some information about how much it degenerates. And if you know something about it, like if it's trivial, then you get some information about solutions of the PDE. So that Joe Cohn introduced the first one. This one was introduced by Alan Nadel for studying some problems in complex geometry. Right, so this ideal is actually, it's coherent in this case. That's one of Nadel's theorems. And I'll state it in more generality in a little bit. But so this is a very particular kind of function, and it's sort of useful for a number of problems to generalize the class of functions phi from just being the log of the sum of squares of holomorphic functions. And so that leads you to the notion of a plurisubharmonic function. So I'm usually just going to write PSH to shorten plurisubharmonic. So what is a plurisubharmonic function? So we'll start with a local version of this. So a plurisubharmonic function is a function phi from u. It's allowed to take on the value minus infinity, not allowed to take on plus infinity. We ask for it to be upper semi-continuous. So that's why you can't take on plus infinity.
Can you draw a little picture to show what that means?
Upper semi-continuity?
Where do you put the point?
Yeah, so the standard picture of an upper semi-continuous function is that if you take the lim sup as you head towards the point in question, then it's less than or equal to the value of the function. So it's allowed to jump up, but not down. This upper semi-continuous function, not identically minus infinity. This is a matter of choice. But the main thing is some kind of, well, there's a lot of definitions of these, but the one I'm going to take is just a shortcut definition. So once you know it's not identically minus infinity, it's locally integrable. And so then you can check what happens when you take such a function, and then you integrate it against the following measure. And you ask for this to be non-negative. This is for all smooth, compactly supported zero one forms. Alpha 1 up to alpha n minus 1. Okay. So, right, once you have a locally integrable function, you can differentiate it as a distribution. So what this says is that you have a current IDD bar phi. Well, it's upper semi-continuous and not identically minus infinity.
Locally integrable?
Yeah. So IDD bar is a closed positive 1-1 current. And it's locally bounded above this thing.
Oh, it is one.
Yeah. Well, after you impose this condition, you'll see in a minute. I'll state some properties. Oh no, before you well.
Because you have to integrate.
Well, you're not allowed to take on the value plus infinity. So if you okay, let me not get bogged down. Let's say after you impose this condition, it will be locally integrable. So let's assume it's locally integrable. All the interesting cases.
Locally integrable.
Let's assume. Okay. Let me assume it's
Part of the definition then, plurisubharmonic.
Yeah. Well, after the fact, yes, there's another definition. Let's assume that that's our definition.
You have to assume it's plurisubharmonic.
Let's assume that it's locally integrable.
Definitions may imply it's locally integrable.
Yes.
Don't have to assume it.
Yes.
Okay.
Okay, so this is a closed positive 1-1 current. That's what this condition means. Yeah, so I'm about to say that. So, e.g., if phi is smooth, then you can calculate this Hessian matrix, complex Hessian matrix. And this matrix should be positive semi-definite. Okay, so that's, but you have to allow it to be singular. I mean, that's the most interesting case for us, is that you want to allow it to be singular. But there are nice approximation theorems for such functions, and they will get implicitly used here.
So these locally interval guides that satisfy this can be approximated by these?
Depends on the space in which you're living, but for example, for a domain in Cn, yes.
And are you saying that this is an if and only if? Like if it's smooth, then it's plurisubharmonic if and only if this?
Yeah.
And there is semi-definite.
That should be an exercise for us, right? Given this definition.
Yeah, right. It's a straight. Sorry, Radu?
No. I mean, above is positive. Positive, and then it becomes only semi-definite.
Yeah, but positive in the measure world always means greater than or equal to 0. It's like French positive. Positif. Okay. Right. So, I mean, one of this definition is equivalent to saying, so maybe this can be a bit more helpful, that this phi is subharmonic on every one-dimensional complex submanifold. Okay, so in general, so PSH. Sorry? What does subharmonic mean? So so subharmonic means that there's a definition and there's a characterization. The characterization is that if you compute the Laplacian in the sense of distributions, it's greater than or equal to 0. Okay. But the actual definition, it's a measure which is greater than or equal to 0. So it's a non-negative measure, positive measure. Okay, but on the other hand, the usual way you define it is you have some domain in the complex plane, and then you have a harmonic function on this domain, and the function is subharmonic. If this harmonic function dominates phi on the boundary, then it dominates phi on the whole domain. Okay? That's it. So it's below the harmonic function that dominates it on the boundary. That's why it's called subharmonic traditionally. Okay. So, well, this condition on the Laplacian that I mentioned, which is also buried in here, it implies so that, for example, if you take a point z in this U and you compute this phi at the point z, then it's less than or equal to the average value of the boundary of the ball of radius r center z of this phi times the a. So average with respect to the area. So you just divide by the area of the ball. So these functions are called subharmonic in general. So plurisubharmonic is stronger. It's subharmonic in every direction. So you have this positive definite thing, and if you take the trace, you get that the Laplacian is actually positive. Okay.
So this is in one variable.
No, this is in all dimensions.
Okay.
It's still true, but this doesn't imply plurisubharmonicity.
It doesn't.
No.
It's just subharmonic.
This is the same as being subharmonic.
The third in subharmonic.
Pluri means if you restrict it to every disk in this ball, this inequality will persist.
Right.
But for subharmonic functions, it need not. It could kind of be true on the average without being true on the individual slices. So, well, so these are the kinds of things you can check. So for a holomorphic function of one variable, say, this is a classical fact everybody learns, this mean value property you learn, and then you can estimate that to get a submean value property.
Log of norm squared.
Right. So for example,
You were thinking it, but you weren't saying it.
no, because I started out by saying that log of sum of norm squared is going to be a generalization of a PSH function.
Okay, I wasn't here for that. So
Okay. So what we know about these PSH things is that this space of plurisubharmonic functions is a closed convex cone. That's obvious. Another thing that you... well, for this statement, it's just there's no topology needed, right? It's just in the space of functions as an additive space. So you take a PSH function, you multiply it by a positive constant. That will be...
no, it's a closed part.
Oh, I see. Yeah. So you're right. So the closed statement. Okay.
You're saying it
Kind of weak topology or something.
It contains 0, but it also contains things on the boundary because of this inequality. So,
With what close cone, yeah.
well, let's just say convex. I don't care that it's closed for this particular. So, in particular, you can multiply it by a positive constant, and it stays PSH. Right. So another thing is that if you have a bunch of PSH functions, phi j, and they decrease towards some function phi, if this function is not identically minus infinity, then this phi will also be PSH. And that comes from checking this inequality, say, on every complex line. And then the third thing that's handy, but I won't really use here, is that if you have any family of plurisubharmonic functions, then you can form the maximum or the sup function over this family, so over all phi and f, phi. So if we call this psi, then this is almost plurisubharmonic. It has to be bounded above. So if it's bounded above, then it still might not be upper semi-continuous. But then you form something called the upper semi-continuous envelope. For example, the value at x is the lim sup as y goes to x of this c. Then this guy will be plurisubharmonic. So you can perform certain kinds of limiting operations on these objects, and they stay in this category. Whereas in algebraic settings, if, for example, you have some polynomials of a given degree, and then you let the degree get huge, these can limit onto horrible objects. But the plurisubharmonic category, they limit onto very nice objects. And that can be very handy. So why would I write this as e to the phi? So far, it doesn't. I mean, if we're interested really in questions about these polynomials, why not just divide by the sum of squares? Well, the reason, well, it's a bit psychological, I guess. But it has to do with the kind of differential geometry that these functions really come from for us. Their history is bigger than that. You know, the subharmonic functions, it came up in the solution of the Dirichlet problem originally by the Perron method. But in this kind of modern, well, the word geometry has been used in at least 4 times in the different four talks. So for me, geometry is going to be some kind of differential geometry of holomorphic line bundles. Okay? So what is that geometry? So let's say, for example, X is going to be a complex manifold. So if you have a complex manifold, it might not have very many holomorphic functions. For example, if it's compact, it doesn't have any holomorphic functions. But in a lot of situations, for example, in the compact Kähler setting, it has line bundles that have some holomorphic sections. So e.g., if let's just say X is projective, so smooth projective variety for this crowd, so projective manifold. And if you could have some holomorphic line bundle on this. And then you could consider a metric of this line bundle. So a metric, it has a little bit of a funny notation. So it's a metric for L is really a section of L star tensor, the complex conjugate of L star. So it's an anti-holomorphic line bundle. And it's supposed to be, so if it's Hermitian, then it will satisfy certain Hermitian symmetries. And then if you have one of these metrics, and L is a complex line bundle, holomorphic line bundle, it has a d bar operator, then the curvature well, is just d bar of this function phi. So what do I mean by that? What I mean is I'm going to explain once what this notation is. So if you have C, a frame for this L, local frame, so meaning a local nowhere zero section, you can try to compute the length of this section with respect to your metric, say the length squared. Okay, and then the curvature will be negative d bar of the logarithm of this function, and it will be independent of Xi. So this is actually the curvature. There could be, in principle, lots of curvatures. So you have to have a connection to talk about the curvature.
Right?
Yeah, well...
change of coordinates.
Yeah, and the fact is Xi has to be a holomorphic frame, too. Yeah, that's right. But, I mean, so this is actually the curvature of the unique Chern connection associated to this line bundle. So the global theory is that these plurisubharmonic functions get replaced by not quite metrics, but what are called singular Hermitian metrics. So a metric, if we view it as a section of this object, we could just ask for it to be measurable or something like that, as a measurable section. So it no longer has the particular meaning of measuring actual lengths of vectors, but it does almost everywhere after some choice. But nevertheless, if this function phi itself, so meaning if this logarithm is locally integrable, if it's locally integrable for some choice of frame, it's locally integrable for all the choices of frames. So then you can still form this object as a current in the way that I said before. So basically, the plurisubharmonic functions, you can think of them as the potentials, let's call phi the potential of this object, of metrics for the trivial line bundle, singular Hermitian metrics, but that have non-negative curvature. Okay.
We worry about these eyes, or
So this, strictly speaking, this is the curvature. I is the thing that makes it Hermitian. This is like one of my colleagues likes to be stickler about these things. I wasn't sure if he was going to be here or not, so I wanted to get it right. So most people just call I dd bar the curvature, but strictly speaking, the curvature is a well-defined thing. You apply the connection twice, and you actually get something anti-Hermitian. It takes values in a certain Lie algebra. So to make it positive, though, you just multiply by I. And so positivity is why the I is there. Okay? Okay. All right. So, I mean, this geometry is going to allow us to solve a certain PDE in a little bit. And I'm going to state a theorem about that. That PDE. Phi is real valued, but dd bar is not. I mean, if you take the conjugate, it reverses the order, and because these are differential forms, you get a sign change. So if you want it to be right, you have to put an I. If you want it to stay the same, you have to put an I there.
One form.
It's a 1-1 form. Curvature for a line bundle is a 1-1 form, or a holomorphic line bundle. Okay, so the reason we call them plurisubharmonic functions, again, is that we can use them as, we can view them as metrics in a certain setting and use the geometry of those underlying metrics to get estimates for a certain PDE that we want to solve. So I'll come back to that. Okay. What about multiplicities? So multiplicities were mentioned in everybody's talk. Well, if we really want to apply plurisubharmonic functions to the setting of singularity theory, we should at least have a notion of multiplicity, and we do. It's called the Lelong number.
Concept pluriharmonic function.
Is he?
Yeah, 42, yeah.
Okay. Pluriharmonic or plurisubharmonic? Both, probably.
Yeah, all of them, yeah.
Yeah, so I imagine that there was people trying to extend the Perron method to several complex variables. It would have come up like that. But I think Oka did a huge amount of stuff. And I guess that was after Lelong invented these. Okay. Okay, so, right, so let me talk about this quickly. So if you have just a single holomorphic function at some point, before I was calling it P, then we can try to define the multiplicity. Well, we can define it. It's the smallest number, smallest order of the derivatives up to which you have any less derivative should be 0 at this point x. So, well, everyone knows what multiplicity is, but it's a theorem of Lelong that this is actually equal to the lim inf as z goes to x of log mod f of z squared over log mod z minus x squared. So if the log of the sum of squares is going to be our object of interest, in principle we would like to substitute that into here. And because I don't have a huge amount of time, I'll just say that can be done. So you can define this with replacing this by a general plurisubharmonic function phi, and this limit still exists. Okay. So it's not a difficult argument, but it's involved. So it uses some version of Jensen's formula in higher dimensions to show that this limit actually does exist. So.
You're saying if you have a plurisubharmonic function that has a long number at any point?
Yeah.
And it can be infinite or something?
And the notation for it, no, it cannot be infinite. It will always be finite.
And is it integer or?
Is it what? Is it an integer? No. So it's not an integer. So yeah, it doesn't have to be an integer. So for example, as I said, you can multiply any of these functions by some constant. And so it will scale according to this constant. Okay. Right. So what this plurisubharmonic theory really gains for us is it gives us tools for constructing holomorphic functions. Okay, so I'm going to start just by stating a theorem. So I'm going to call this Harmander's theorem. Because morally, this is Harmander's theorem, but the statement it wasn't just proved by Harmander, it was proved simultaneously by Andreotti and Vesentini. And the statement I'm going to put here is due to Skoda. Okay, so this is going to be a Stein-Kähler manifold. You have a holomorphic line bundle with the singular Hermitian metric e to the minus phi. So assume there exists some 1-1 form, well, theta greater than or equal to 0, 1-1 form. In practice, it should be bigger than 0 almost everywhere, such that, if you like, you can think that it's bigger than 0. It's good enough for most applications, such that, so the curvature. Sorry?
It's supposed to be an honest.
Smooth, yeah, honest, smooth form. Yeah. Or at least, not a current. So it could be not smooth, but it shouldn't be a current in the sense that when you integrate it against some forms, it shouldn't differentiate them. So measure-like object. But let's say smooth. IDD bar phi plus the Ricci curvature omega should be greater than or equal to this smooth form theta. Then for all so let me say 0Q forms, but I mean really just measurable 0Q forms for the moment, but they're going to be an integrability condition. For all 0Q forms, alpha, so here I need Q to be at least 1, such that, so I want this alpha to be d bar closed. So I guess I need them to be locally integrable to define this. So this is in a sense of currents, d bar closed. And so the integral of this alpha, and now I'm going to write something strange. If it's a 0-1 form, you can just think of this theta as a metric, and measuring the norm of alpha means you have to involve the inverse of the metric. So if it's not invertible, you need this to be 0. This is why in practice it has to be invertible almost everywhere. If it's a higher form, then you have to do some contraction with the Kähler metric as well. But it doesn't matter too much what this is. So, so I missed something here. This should be L-valued 0Q form. So values in this line bundle. And we want this integral to be finite. So for all such things that are integrable, there exists a 0Q minus 1 form. So for example, if Q equals 1, it's a function. So, and again, L valued, so it's a section of L. U such that d bar U is this alpha. And moreover, we get an L2 estimate for U. So this is really with respect to omega. And then, yeah, it's bounded by that norm Okay, so you
Whole Stein manifold?
yeah, in the whole Stein manifold. So this is a kind of vanishing theorem, if you like. It's a quantitative vanishing theorem. It tells you that if something defines a cohomology class, that cohomology class is trivial under these conditions. This is a kind of cohomology vanishing.
Does 0Q mean QDZs or QDZ bars?
DZ bars. So it's a cohomology vanishing with estimates. So a lot of times. Well, okay. So the idea is that this alpha is going to be the error from constructing a holomorphic object. So if you take some smooth function that has certain properties, you would like it to be holomorphic. You take d bar, you find it's non-zero. So you want to find a u so that d bar u is this alpha. If you subtract that u, then you will have a holomorphic thing. But you could do that on a Stein manifold very easily. The problem is one of the solutions is the function you started with. So then you get 0, and you're nowhere. But the point is that this estimate can often help you guarantee, for example, if this guy is very close to being holomorphic, but it's really not small, then this u will have a very small L2 norm, so it's extremely unlikely that it will be the same guy that was close to being holomorphic. Okay? So that's the idea behind it.
From any point of view, a 0Q form is the thing that represents coherent cohomology.
Yeah, right. So it is the Dolbeau isomorphism.
Yeah.
Right. So, but since there are a lot of algebraic geometers here, I'll state a consequence of this theorem. It's more, you have to do more work than just use this theorem, but this theorem plays a crucial role in Nadel's theorems about multiplier ideals. So Hermander's theorem is crucial in the proof of the following theorem due to Nadel. So, well, let's say, I mean, it's true in great generality, but let's say that X is either Stein or projective. And let's say we have a holomorphic line bundle L and a singular Hermitian metric SHM, and we want its curvature to be, for simplicity, let's say that it really is non-negatively curved. So it's a global generalization of a plurisubharmonic function. Okay? Then there are two statements here. One is that the multiplier ideal sheaf. So, as I said, this. Well, okay. So this metric phi doesn't give you a globally defined function, but the multiplier ideal is a local construction. Still, to define it, you have to choose some frame. But if you choose any other frame, the function you get differs from the previous one by a smooth function. So it doesn't change the singularity, so the integrability will hold either way. So this is well defined depending just on the metric or equivalently just on its curvature. Okay? So no, it's singular Hermitian metric.
S is singular.
Yeah, it's funny. Singular Hermitian metric is allowed to be smooth. So it should be called a PSHM, possibly singular Hermitian metric. Yeah, so it's a singular Hermitian metric. Otherwise, I just say Hermitian metric. So, okay, so this I, of course, if it's smooth, then this is a trivial ideal, so it is coherent.
These assumptions imply that X is scalar?
Yeah, both of them imply that X is. So Stein means a closed submanifold of Cn.
Right.
Okay.
Oh, yeah.
Projective is Kähler.
Yeah.
You do need Kähler for Hermander's theorem. You need Stein in principle, but not always. There's ways of getting around it. But for example, a projective manifold is very much like a Stein manifold. So what you do is remove a hyperplane section, and the resulting thing is Stein. But because everything you do has L2 estimates, you can extend all the solutions of your PDE across this divisor because the L2 bound allows you to do that for various reasons. So once you can do it on a Stein manifold, you can do it on a projective manifold. But if you're already on a projective manifold and you have a smooth metric, Hormander's theorem's proof is even easier as a consequence of the Hodge theorem. So, but not the Hodge theorem that most algebraic geometers end up walking away with. There's actually a theorem that tells you how you can solve the equation, and it gives you estimates. Okay, so, right. So this is a coherent sheaf of ideals.
Of the hard limits, yeah. Hot used it.
Okay, and then now I want to also introduce a vanishing theorem that throws away much of the excellent estimates that we have here, which is called the Nadel vanishing theorem. But for that, I need a little bit more hypothesis. So if also I dd bar phi is greater than or equal to some Kähler form, and here I really want x. No, I don't want. I think Steiner projective still works. So if this is greater than or equal to some Kähler form, so there's a name for a line bundle that admits a singular Hermitian metric with a lower bound on the curvature by a Kähler form. Those are called big line bundles. Write it in big letters. Then hk of x, if you take the multiplier ideal, and so you're looking at sections of this line bundle. This is the canonical bundle. You're looking at sections of this line bundle whose coefficients in terms of a holomorphic frame live in this ideal sheaf. So this will be 0 for all k. Maybe I should write q to connect with the previous q. So it almost looks like this theorem's already proved in there. But I mean, with this, here you have to use the Dolbeault isomorphism. And when you do that, it's you have to be a little bit careful about what kind of sheaves you use, because there is buried in here a local L2 estimate. There's not a global one, but there's a local L2 estimate. But it's pretty easy to set up the right sheaves and use the abstract Theorem theorem to conclude this as well. So, okay. Okay, so that's one of the tools for constructing holomorphic functions. And maybe through this theorem is how most of you would have used it to construct holomorphic sections. Another tool is the L2 extension theorem. And this theorem is a difficult theorem. Okay, so there is a very general version of the theorem that I was going to state, but in the interest of time savings, I'll only state the ones that I really want to use. So it'll be more local and maybe slightly easier to understand. So, so let omega in Cn be a pseudo-convex domain. So for the applications here, you can even, if you don't know what pseudo-convex is, you can assume that it's just convex. That's good enough for the applications here. And then I'm going to let Z be a hyperplane. So I'll put it in omega is the intersection of omega with a hyperplane. Oh yeah, sorry. It should definitely be bounded for this. Yeah. So bounded pseudo-convex domain, and then you intersect it with some hyperplane So if I said you should think of it as convex, let's do that. Think of it as convex, and you have some hyperplane in there. And then let's take our line bundle will be the trivial bundle. So we're just going to have phi, a plurisubharmonic function on omega. And let's assume that the restriction of phi to this z is not identically equal to, which could happen, it's not going to be identically minus infinity. Okay? Not identically minus. Thank you. Okay, then for all g holomorphic functions on this z, there exists some capital G which is holomorphic on omega such that, so this G restricted to Z is equal to G. So all this has nothing to do with a plurisubharmonic function, and up to this point this is true for any pseudo-convex domain or any Stein manifold in Z, a closed submanifold of it. But the crucial thing here is an estimate, which is that the integral of g squared e to the minus phi, let's say with respect to the Euclidean metric on omega, is less than or equal to, and there's a very nice constant here, it's 2 pi times the diameter of omega times the integral over z of g squared e to the minus phi. Let's write dA for the measure restricted to z. I mean, it's still the Euclidean volume form on z, provided that this right-hand side is finite. I mean, if it's not finite, it's still true, right? Because it doesn't, you don't get any information on the L2 norm. But anyway, so it looks like an innocent statement, but actually it's extremely difficult to prove, and people for a long time were not even sure it was going to be true. It was discovered by some accident. What's that? Oh, this theorem is due to Osawa and Takegoshi. That's what you hear, the Osawa-Takegoshi extension theorems. Yes?
How is it? How are the theorems discovered?
I think so. There was a very different kind of result by Donnelly and Pfefferman. They were actually trying to get some other kinds of cohomology estimates for domains in CN. And they had this Annals paper. Osawa tried to read it. And he said he didn't understand it, but he somehow managed to extract enough of the argument to prove this statement. And he doesn't really know how it happened. So, yeah. Well, I mean, you have a convex domain in Cn, and you take any 2 points, and you can measure the distance between them, and then take the largest distance you're going to get. That's usually what's... Right. So that's why, in general, the constant is something else, and the L2 norms are something else. But this is all I want to do here. So, yeah, okay. So, I mean, essentially, how does this theorem construct holomorphic functions for you? It's done by induction on the dimension. So, in one place where it's very easy to construct holomorphic functions is on a point. Right? It's a very, very easy problem. And so, now suppose you want to extend it to a one-dimensional thing. Well, you just take a disk and have a point in the middle, and this theorem will tell you have an extension with nice estimates on the norms. So, and now you apply this again by induction and keep growing the domains. So, and the proof of these two theorems, they have a lot of relationship between them. There's actually some other proofs of this theorem relatively new that make it almost equivalent to this theorem.
So just make on the
I'm going to show you now, so the next thing I want to talk about. This is actually going somewhere. Hopefully I get there in time to still go to the holiday party. So next thing I want to talk about is Bergman kernels. So it looks like I'm taking a big detour from plurisubharmonic functions, getting further and further away from them. But okay, so suppose you have some Kähler manifold with the holomorphic line bundle and a singular Hermitian metric, e to the minus phi. And let's just assume that, for simplicity, that I dd bar of phi is greater than or equal to some smooth form on X. Any smooth form on X is fine. So then with this data, you can actually make some L2 spaces. So the first one is, I'm going to call L2 of phi. You just take all the sections, measurable sections, of L such that, and then you integrate them and expect the integral to be finite. So you measure the point-wise norm, integrate with respect to the Kähler volume, and you want this to be finite. So this is some huge vector space, but it has a subspace. So it has a subspace which I'm going to call H2 of phi, which is just this space, the elements of this space that are also holomorphic sections. Okay, so it turns out that under these conditions, this is a closed subspace. So this is in L2 phi, so it's a closed subspace. Now, the reason it's closed is because point evaluation of holomorphic functions is a bounded operation with respect to the L2 norm. So that's just the submean value property for absolute value squared of a holomorphic function. Then when you have this weight, if it's locally bounded above, you can write this f as f squared e to the minus phi e to the phi. And if you have a locally bounded above, this thing will come out as a constant. And that constant will appear in the local bound for pointwise evaluation. Okay. So anyway, that's why this is a closed subspace. It's because once you have locally uniform bounds, you can apply Montel's theorem to a sequence of holomorphic sections, and you obtain a convergent subsequence, which is holomorphic. Okay? So the limit will be holomorphic. Okay, so what that means, when you have a closed subspace of a Hilbert space, you have a projection operator. So a bounded orthogonal projection operator. Let's call it P phi from L2 phi into this H. Okay, so how do you do that? Well, suppose you want to project a smooth section, P phi of some H, smooth section H. So how do you evaluate that at some point X? Well, here's what you do. You first choose for this space some orthonormal basis, okay, with respect to this L2 norm. You choose an orthonormal basis, and then you take your H and you project it onto, so let's write this, H of y, f j of y bar, e to the minus phi of y, dv of y. And that's the component of H in the direction fj of x. And then you sum over all the j's. This could be a finite sum if x is compact. Right? So then these spaces are finite dimensional. But let's just write it as a sum over j. Okay, so let's write this as some kind of tensor, just for kicks. And then well, it's some magic about convergence, but it's true that then you can write this as h of y, k sub phi of x and y, e to the minus phi of y, dv of y. this dv omega. And so where this k, the formula for this k of x and y is just the sum of fj of x tensor fj of y bar sum over j. And if this were convergent, it's actually a holomorphic section of, if you put the right complex structure, this is this box times okay, and it does converge, again, because point evaluation is bounded. But if you don't really care too much, in most of the situations, not most, but some of the situations you apply this to, this x is compact, and then it's a finite dimensional thing. But let me give you kind of another moral reason why this is convergent. I mean, one of the things that's obvious is if any such formula were true, it doesn't depend on the choice of orthonormal basis. You're just projecting onto a subspace. And so you can choose any orthonormal basis of that subspace, and you will get this projection. So, okay, so here's a good way to choose a subspace. So suppose you want to evaluate this, k at this point z. Okay, so what you do is you choose the following orthonormal basis. First, you look at all the sections that vanish at the point z. Because point evaluation is bounded, this is either everything or a hyperplane. Okay. So if it's a hyperplane, you take an orthonormal basis for that hyperplane, and then you have one complementary direction. That's given by the Riesz representation theorem. That's why it's a hyperplane. So, and then the one complementary direction is the only element of this basis that doesn't vanish when you plug in z. So it means that with that, if that element is f, then this is f of z tensor f of w bar. So that's actually the value at a point. But if you move the point, the function also changes. So anyway, another way of saying this is that this k phi of z, let me put bars here, e to the minus phi of z, this is actually the supremum of all the numbers, say g of z squared, e to the minus phi of z, where you take this supremum over all g holomorphic, so g in h2 phi, with the norm equal to 1. Okay. So this Bergman kernel is a consequence of some kind of solution of a extremal problem. So what that automatically tells you is that you have a lower bound for this object as soon as you can construct a holomorphic function with a lower bound on its L2 norm.
Why is that true, the last line? Is that obvious?
Well, okay, it's almost obvious, but not quite obvious. So the first thing is that it actually, according to this, is actually realized by a single function. Right? But on the other hand, suppose you have any holomorphic function with unit norm. Then you can complete it to a basis. And then the Bergman kernel is greater than or equal to the sum of squares of this plus the rest of the basis. Right? So it's almost obvious, but not quite. Okay, so what I want to say now is that this thing has an upper bound because each of these elements, by the submean value property, is bounded above. And the upper bound, I'll write it down in a moment when I write Desmailly's approximation here. But at least it's believable that the pointwise, if the pointwise norm is controlled by the integral over some small ball, then it's also controlled by the integral over a larger, the whole space. So you get an upper bound, and then the lower bound means that you actually have to find some function with a good with a good point-wise estimate. And that's where this Osawa-Takegoshi theorem comes in. Okay. So and the other thing about this is that you notice that when you evaluate this on the diagonal, it's really a sum of squares of holomorphic sections. So in particular, I mean, this k phi of z, z bar e to the minus phi of z is equal to the sum of some fj of z squared e to the minus phi of z. And if you have an upper and lower bound for this thing, it means that the k itself is very closely related to e to the phi. So this is going to give us an approximation of phi in terms of sum of squares of holomorphic functions.
But do we have any homomorphic functions?
For example, on some spaces you do, in some spaces you don't. I'm going to write one down now where you do. So this is Desmaillet approximation. Okay, so there's many versions of Desmaillet approximation. I'm going to state one of the second weakest one, but it's good enough for what we need. So let's let phi be PSH on a bounded pseudo-convex omega in Cn. And so that allows us to make the following Hilbert space. We've made this H2 a phi, but now I'm going to do something a little bit different. Instead of phi, I'm going to use a huge integer multiple of phi. Okay? And so in here, I can choose some orthonormal basis. And now I'm going to let phi sub n of z be 1 over n log of this Bergman kernel. That's the holomorphic L2 things with the weight e to the minus n phi. No, it's gone. So you want me to write it down again?
No, good.
Okay. Right. So essentially, because of what I said about bounding this Bergman kernel, and I unfortunately have to go a little fast, you get the following result. Then there exists numbers a and b, positive, independent of n, such that for any point z and omega, and for any r that's less than the distance from z to the boundary of omega, you have the following estimate. So phi of z minus a over n is less than or equal to phi sub n of z is less than or equal to the sup, and this comes from the submean value property, sup z minus zeta less than r of phi of zeta plus 1 over n log b over r to the 2n. Okay, so this is what you get from the upper and lower bounds. Well, at least the upper bound you get from this. For the lower bound, you need a particular function. So, as I said, and the Osawa-Takegoshi theorem gives it to you, but maybe for shortage of time, I'm going to skip the details of that. But, okay, so in particular, this gives you a little bit more information. It tells you that this, you can also compute the long numbers of these phi and phi n. C over n. Maybe it's n over n. N over n. Yeah, so there's this n here, precisely because I want to get this. So I'm going to say a little more clearly what this says in just a minute. But you get this estimate for the Lalong numbers by dividing these things by log mod z minus zeta minus z squared and taking the lim inf. That reverses the inequalities. And also, it says that this phi n converges to phi pointwise and in L1 loc. So it's a rather weak convergence, but still useful for a lot of stuff. Okay, so what have I said here? It basically, so these functions phi n, they are almost like the functions we started with. Right? These functions, this phi n of x is of the form 1 over n log of the sum of fj of z squared. These fj's are determined by the phi through some Hilbert space construction. But more importantly for us, these are the kinds of plurisubharmonic functions we got trying to study singularities in algebraic geometry. Then we generalize them to something, but on some level, the generalization just is very well approximated by the original situation, as long as you allow yourself some division here. So this leads to a lot of the asymptotic theories that you have. The sum is infinite here, but that's not such a big deal. So for example, there's a global version of this. So if you're working on a compact manifold, then the sum is finite, but these are sections. And there's actually ways to pass back and forth between them. So in any case, at least morally, it shows that the plurisubharmonic situation, which initially might have looked very far from the algebraic situation, can actually approximate the algebraic situation in a certain sense that can be very useful. Okay, so in the last 7 minutes, I want to use all these tools. Well, I'm not going to actually have time to prove anything, but I want to talk about this complex singularity exponent. Okay. So all the results that I mentioned have some application in the proof of some theorems, in the proofs of some theorems in the complex singularity exponent.
Number is analogous for canonical.
No, sorry.
Oh, the multiplicity.
All right, the long number is the analog of the multiplicity. The next thing is to give the analog of the complex singularity exponent, which is the complex singularity exponent. Okay, so here's a definition. So this is a complex singularity exponent. Here's a definition. So you start with any complex manifold. Take K a compact subset of X, and phi a plurisubharmonic function. Maybe I should say it like this. Phi PSH. Then, for any compact subset of X, we define Ck of phi to be the sup of all the numbers c greater than or equal to 0, such that e to the minus c phi is an L1 loc of U, where U is a neighborhood containing K. So the case we've been looking at here has been just the case of a point. Everyone discussed it on some level. Okay, so I was going to...
He is blowing up on K or something?
That's right. So it's meant... Well, potentially blowing up.
Yeah.
It's blowing up somewhere on K. And then we want to see, how much do we have to shrink phi so that even though it's still blowing up, it's integrable. So it's just the same as what people have been doing at points. And in fact, it's computed by taking the inf over all the points. So really, this is the most interesting one. So there are all kinds of things to say about this that have been said already. So it really does give you the same quantity by definition if phi is log absolute value of a holomorphic function squared. And so again, if that function is smooth, then the number you're going to get is 1. But otherwise, it's not always going to be 1. Most of the time, going to be much less than 1. It gets smaller as phi becomes more singular. But and then what I was going to do was to calculate it, but Rob luckily did that earlier. So if you have an ideal, then you can perform the Hironaka log resolution package on the ideal and compute and see that it's a rational number. But it's absolutely not rational for general phi because Cx of a phi is a Cx of phi. So it's not going to be a rational number. So, but there's another, so because I was going to mention two things. So one of the things is that there's a certain semi-continuity theorem for this. So I just want to mention it briefly. So Desmailly Collard semi-continuity. So you can look at the thing that associates to phi, to say the complex singularity exponent. It could be on a compact set. Ck of phi. And then you have to put a topology on this if you want to say that this is semi-continuous in some way. So I'm going to say that it's lower semi-continuous. So you just have to put a mirror under the picture that I gave before for the upper semi-continuous to see what lower semi-continuous is. But the topology here, so this is the space. So this is the space of PSH functions with the L1 loc topology. And there's even stronger versions of this semi-continuity. So in the last couple minutes, let me mention the relations. Well, I already mentioned that it's not a rational number, so it's not necessarily exactly going to have all the PSH version is not going to have all the properties of the algebraic version. Yeah.
Now let's say that I take phi to be log some absolute value of polynomials.
Okay.
What does this statement actually say in that case?
Well, if you let those polynomials converge uniformly on compact sets to some other polynomials, then this number could jump down in the limit.
So let's say that k is just 1.
Right. So if you compute this number for you have a sequence of such polynomials. Okay. So and you compute this number for that sequence, and now you take the limit as those.
My question is rather, so what's the meaning of the convergence in terms of polynomials? What does it mean?
So it means that they converge. So for example, they could just converge uniformly on compact sets to some holomorphic function or some other polynomials.
Compact sets in the point or what?
Yeah. Yes. In the neighborhood of the point is enough. Yeah.
So is what you're saying, like if I take some sort of like one parameter family declaration of singularities, then they can't become much less singular all of a sudden, but they could become.
No, they do become more. Yeah, more singular. Yes, more singular. Yes.
Can't magically become much.
But you have to be careful what you say about what a one-parameter family is. So
yeah.
that's right. Yeah.
But
The singularity could get worse, but not better.
yeah. Okay. Great.
Is it okay, Mirchan?
Yeah. So
Okay. Okay. So, well, one of the consequences of the rationality of these numbers when the phi comes from algebraic data is that if you have some c, so that e to the minus c phi is in L1. Let me say it like this. So it's just, let's say it like this. So if this phi is algebraic, let me put it in brackets, okay, and e to the minus phi is an L1 lock, then that implies that e to the minus 1 plus epsilon times phi is also in L1 lock. So it's this picture that Kevin drew. So if you have your complex singularity exponent, the non-integrable part will include the endpoint. So if you're integrable here, you'll be integrable for a little bit more. So it means that the locally integrable locus is open on the right. So now that's true in the algebraic case, and it was posed as a conjecture by Desmailly, and Desmailly and Collard, in fact. And it's called the openness conjecture. But that was also proved to be true. So the theorem
follows just from rationality, doesn't it?
Right.
It follows from the proof of rationality.
Yeah, I guess. I mean, let's see.
Yeah.
Yeah, it probably does not follow just from rationality. It follows from proof of it. Yeah. So in the algebraic category, you can see very clearly, if you put this complex singularity exponent here, it will not be integrable. And then that's the question here. So, and the theorem is that e to the minus, let me just say it like this, cx phi times phi is not in L1 loc. Say it like that. Okay. Right. So this was actually proved by Bo Berenson. And I had a very ambitious plan to show you a very short proof of this using Osawa-Takegoshi theorem. But, you know, my PhD advisor when I was a student told me, never go overtime in a lecture, because as soon as the clock hits 5:15, the only thing your audience will see is red. So let me stop here.
Any questions? Well, thanks again. Thanks everybody.